Welcome, mathletes, to section 7.2, solving exponential equations and inequalities. We're going to need that Inspire, so go get it. If you don't got it, this whole chapter we're going to use in the Inspire, I'm pretty sure. Not a whole lot of graphing here, but we are going to use it towards the end of the word problems. Let's review a little bit. So if we simplify this, x squared times x cubed, although we're multiplying the bases, we're adding the exponents. So 2 plus 3 is 5. Here, let's switch over to multiplication. This is a power raised to a power. U squared multiplied by itself 3 times. That would be 2 times 3, which is 6. There's no exponent written here, but you can write one in if you want. A cubed times a is a to the fourth, because 3 plus 1 is 4. And here we'll switch back to multiplication, because we're taking a power raised to a power. 5 times 2 is 10. 9 plus 2 is 11, and 2 times 7 is 14. That's your review, and we want to make sure we know when to do what to do. You add exponents when you multiply the bases, and you multiply the exponents when you raise a power to a power. Here's a second review we got to look at here. If this is a linear table, what equation represents this table? We have to find y equals mx plus b because it's linear. We can see it's going to be linear because every time you add 3, 2 plus 3 is 5, plus 3 is 8, plus 3 is 11. So because you're adding 3 every time, we can say that the slope is 3. And looking here, the y-intercept is going to be 5, because when x is equal to 0, y is equal to 5. And that's how we get the b value here. So we find the y-intercept by the y value when x is equal to 0. You look on the table, where is x equal to 0? Boom. And there's the y value. That's going to be the b right here. And you're going to find the slope by what's the change in y. 8 minus 5 is 3. Let's solve some equations. Okay, so here's an exponential equation. The goal for today is to figure out how to solve exponential equations and some inequalities too. So here's an equation, and you can see there's exponents here. 2 to the 3x plus 1 is equal to 2 to the 7. Well, the only way that these are going to be equal to each other, because the bases are equal, then the exponents have also got to be equal. And so we can go from an exponential equation just down to an equation that has no exponents at all, simply by saying the exponents have got to be equal to each other. 3x plus 1, 7. 3x plus 1 has got to equal 7. When you undo the addition and multiplication, you get x equals 2. Same thing here. Bases, check to make sure first bases are the same, and if they are, then that's great. You can say that the exponents have also got to be the same. 5x minus 2 is equal to 18, and so therefore x is equal to 4. Here, negative x, 3x has got to equal 3x minus 4 because the bases are the same, and therefore the exponents have got to be the same. You set them equal to each other, and you solve, you get x is equal to, why don't you tell me? Preliminary step. So first make the bases the same. You can see here in this next set of equations, the bases are not the same. And that's okay. And it's going to be easy enough here, and not easy, but it's doable that we can actually change the bases. If the bases are not the same, then we can change them to make sure that they are the same. So therefore, 9 and 81, I think we can make this 81, turn it into a base of 9 instead, because then bases would be the same. We can do what we did up here. 81 is the same thing as 9 squared. So we can say 9 squared, and it's all in parentheses here, 9 raised to the second power raised to the 3x plus 6 is going to be the same thing as what we had before. But now remember that, as we set up here, r to the 5th to squared is going to be the same thing as a 10. So we can multiply if we are raising a power to a power, then we can multiply the exponents. So therefore, it becomes 2 times all of this, 2 times 3x plus 6. And now we can set the exponents equal to each other, because the bases are the same. When you set them equal to each other, it looks like this, and when you solve it eventually, I didn't show the work because I know you can do it. This is x equals 8. Let's do the same thing. Let's practice this preliminary step of first making the bases the same a couple more times. 4 and 8. Well, 4 times 4 times itself, no easy number of times is not going to be 8. So 4 times itself once is 4. 4 times itself twice is 16. And already we've overshot 8. But I think what we can do is take this same skill, the same idea, and apply to both sides of the equation. These are both powers of 2. So 4 is 2 times itself twice, and 8 is 2 times itself 3 times, 2 to the third power. So you can see the base that we've got to make is 2 on both sides. And we're going to apply the same trick here. 2, since it's raised to the second power raised to the 3x minus 3, we can multiply these exponents here. Again, the exponents multiply, and this is what you get. So now that the bases are the same, we can set the exponents equal to each other, and this is what you get. And when you eventually solve all that algebra 1, you get x equals 1. Same thing. I know that 9 times 3 is 27, but 9 times itself, no easy number of times, is going to give you a number. It's going to give you 27. So we're going to do the same thing here. We do recognize that 3 times itself twice is 9, and 3 times itself 3 times is 27. So we can say that this is the common base on both sides of the equation is going to be 3. 3 raised to the second power, again raised to the negative x plus 5 is going to be, you're going to multiply these here. So therefore you get this, and when you set exponents equal to each other, you get this, and when you do all your algebra 1, you get this. Big idea. So when solving exponential equations, make the bases the same, and then set exponents equal to each other. If you wanted to write it down as a property, you could say the property of equality for exponential equations is this: b to the x is equal to b to the y if and only if x is equal to y. The exponents are going to be the same. Now, some caveats here. We've got to make sure that b is greater than 0, and the base here is 2, the base here is 3, the base here is 6, the base here is 9, 4, 9, and 3. They were never, 3, the base here was 9, the base here was 2, the base here was 3. In any case, b was always greater than 0. We're not going to talk about negative bases in this particular chapter, and the base is never equal to 1. It's always greater than 1. It's or in between 0 and 1. It's like a fraction. We could have the base be 1/2 if we wanted to. So let's that's solving equations. Let's also talk about tables right here. You notice that this was plus 3, plus 3, plus 3 to get the slope. Well, we're going to do the same thing with multiplication. So we get, you notice I'm looking at this table and I go 1.5, and then to get to 3, to get to 6, to get to 12, you're doubling every time. 1.5 times 2 is 3, times 2 is 6, times 2 is 12. And applying the same idea here. Alright, and by the magic of pausing the video and changing things, I'm actually going to write the answer here. So it's going to be in the form of y equals a times b to the x. Just like before it was y equals mx plus b, here's your exponential version. That was a straight line. This is what an exponential curve can take the form of. Y equals a times b to the x. You're going to find the a value right here. When x is equal to 0, the a value is going to be 3. Boom. And then instead of adding, we're going to be multiplying. So every time you multiply by 2, and that's going to be the base right here, 2 to the x. A times b to the x. The base is 2, and the vertical dilation is 3 over here, the a value. Again, you can check out where x is equal to 0, and then the y value is 10. You put it right here, and then multiply by 3, you get that. You can actually check out the table. I'm going to go to b graph, and then I'm going to type in 3, for this first example, 3 times 2 raised to the x power. Why don't you try it with me? Boom. There's that curve. We graphed those before by hand. And now you can graph them on your Inspires just to check as well. And I'm going to make a table, Control T for table. And so you can see on this table, I'm getting the same values. Go up 1 or 2. We get 1.53612. 1.53612. So it checks out. I'm gonna go Control T again to hide the table. I'm gonna press Tab and go up to edit this equation again. And so here we're gonna go 10 times 3 to the x. Change it to 10 times 3 to the x power. Graph it. You can see it's a bit steeper. And Control T for table. Boom. And so you can see we got the same numbers we're looking at. 10/3 is the same thing as 3.3333. And it goes up as high as 90 right here. So that's what that looks like on the Inspire. Here, the y value, when the x value is 0, the y value is 16, so it's 16. And it's being multiplied by 1/2 each time, which is the same thing as dividing by 2. 32 divided by 2 is 16, or times 1/2 is 16, times 1/2 is 8, times 1/2 is 4. And so you can see, let's take a look and see what that looks like on the graph. see, control, I'm going to actually click over here in the white space. I'm going to press tab. I'm going to press up. I'm going to change it to not 3, but parentheses 3, 1 divided by 2. And then the starting value is 16. Boom. Okay, and you can see it's flipped horizontally. Now it's now decreasing, and it will approach to 0 as x approaches in positive infinity. And all the small numbers are over here where the x values get higher and higher. The table looks like this. Here, there's a 32, 16, 8, 4, 2. You can make sure you can get these tables as well. Here, the y value is 5/4 when x is 0, so that's what goes first, 5/4, and then you're multiplying it by 2. 5/8 times 2 is 5/4, times 2 is 5/2, times 2 is 5, times 2 is 10, and you can get the same thing on your Inspire. Here, when the x value is 0, the y value is 20/3. Ooh, 20/3 as the a value, and then you're multiplying it by 1/3 every time. So 20 times 1/3 is 20/3, times 1/3 is 29th, times 1/3 is 20 over 27, and this is 20/3 times 1/3 to the x power. You find the y-intercept a by the y value when x is equal to 0, and you find the base b by whatever you're multiplying by repeatedly over and over again. You remember these formulas, exponential growth from last time and exponential decay from this time. We're going to do some word problems. Okay, Super Bowl. Since it began, wait, I gotta get some tea real quick. Since it began in 1966, excuse me, the extremely high viewership of the Super Bowl has led companies to pay millions of dollars to advertise for just 30 seconds. The average cost of a 30-second advertisement during the Super Bowl can be approximately modeled by an exponential function, where the initial cost is $58,000 and the average cost increase by 9.9% each year. When did a 30-second ad first surpass 1 million? We're going to do these two ways. We're going to do it calculationally and then also on the graph. So if you were making a table like this, when x is equal to 0, the y value would be $58,000, the initial cost back in 1966. So we're going to let p equal 58 here. $58,000. I'm going to do this on the calculator first. So, and then we're going to multiply it by. Let's see. I'm going to get the enter, and now it's an answer. And now I'm going to multiply the answer by 1.099. That's 9.9%. 9.9% each year, an increase of 9.9% each year. So that's 1966, and I think we're going to use t is equal to 0. This is the year 0, which is 1966, and now this is year 1, year 2, year 3, year 4, year 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. We're getting close to 1 million. 31. Okay. In 31 years, it'll surpass $1 million. That's how you do it on the calculator. If you wanted to, you could also look at the graph. So let's actually graph this as a function right here. That's a little, what we did here is a little bit arduous, and if you misclick or miscount, by 1 year, you could be off, and the answer would be wrong. So let's actually do it a better way. We're going to go to the graph. Here's another button you can press. Graph. Scratchpad. Graphing. Scratchpad. That's a fun button to use. Okay, so we're going to go to we're going to press tab, and then we're going to press up. It's a function 2. I'm going to edit this function 1. We want it to be, let's do it in thousands of dollars. 58 right here. So the y value is going to be in thousands of dollars. I'm not going to type out all 3 zeros. It's just a little arduous. So you need to change this to 1 plus 0.099. That's 9.9% written as a decimal. You can see it's a 1 plus there. You could write 1. You don't have to write the plus. You could write 1.099 also if you want, and that's x. Okay, so you can see, well, where to go. I don't know. I don't even see it on the graph. Let's zoom out a bit. Menu, zoom, with 4 windows. Zoom, 4, zoom out. And let's make this the center. Zoom out, zoom out, zoom out. Oh, there it is. Okay, zoom out, zoom out. Okay, so it's getting really high. Maybe it'd be easier to see on the table. So you can see year 0 is 58, and then year 1, 2, 3, 4, 5, 6, 7. Let's just scroll down a whole bunch, and we get to, all of a sudden, we get to 1,000 thousands, which is a million. It's going to first surpass $1 million in year 31. If you wanted to, we could go here, and let's press tab, and let's actually type in 1,000. And we can't see it because it's just not high enough. But there it is. And if you wanted to, you could find an intersection point. Oops. I just made an error, and I paused the video and I was going to correct it, but I figured maybe now is as good a time as any to show you how to correct an error. Here's a couple things you can do. You could double click on this and manually enter it, or if you wanted to, you could also press, here's the undo button on the Inspire. It's really handy to have, and I'm sorry it took me 7 chapters to show you the undo button, but here it is. You can do Control, and then this blue undo arrow right here, it looks like that, and it goes back to where it was, 1,000. Anyway, you can find an intersection here. I'm not going to spend the time doing it at the moment. Maybe I'll do it on the next problem, but this is how high it is, and this intersection is at x equals 31, y equals 1,082. So 31 years since 1996, which brings us actually to the present year of 1997. I really do recommend translating a problem into easier numbers, like 58 is way easier than 1,000, and 31 is way easier than 1966, because the numbers just get too unwieldy to use conveniently on a graph or in a table. The moment you drive the car off a dealer's lot, it begins to depreciate or lose its value. We did a problem like this last class. In 2017, the average price of a new pickup truck was $41,000. It depreciated by 9% every year. How many years will it be worth? In how many years will it be used? 20,000 or less. So we're going to use easy numbers, 41, not 41,000. The rate is going to be that it depreciates is 0.09. That's 9% written as a decimal. And you can see we're going to be subtracting. 1 minus 0.09 is 0.91. T is going to be 0 in 2017, and there's a real error. T is going to be 0 is going to be years since 2017, and then so therefore the formula is the p-value, the initial starting principal of $41,000 times, and the growth factor is going to be 0.91. It's to show you exponential decay. We did the subtraction. 0.91 raised to the t, and we really want to know when is that going to be less than or equal to $20,000 here. So to find the answer of that, I'm going to press tab. I'm going to, let's see, this needs to be $20,000, enter, and then we're going to press tab, and then we're going to say this needs to be at 41, and then this is going to be minus 1 minus 0.09, enter. Okay, so let's take a look, and let's zoom back out. Menu, Windows zoom. No, let's go to the standard, and now we can zoom back out from here. Windows zoom, out, click. Oh, there it is right there. Let's actually find that intersection point. So menu, analyze graph, intersection. You can see the text right here says lower bound. It's going to show me a couple dotted lines, and you go lower bound, upper bound, intersection. At 7.61, is that intersection. It'll be $20,000. Looking at the table, you can do the same thing. When is going to be less than $20,000? Right here, between year 7 and 8. So after 8 full years, then it dips below the $20,000 mark. So then 2017 plus 8 is 2025, which is coming up. Thanks, y'all. I just want to drop in here that um, my favorite movie, my favorite fantasy movie is Lord of the Rings. Way better than any other wizardry or other fantasy movies out there. So Lord of the Rings, lots of fun, lots of Academy Awards. Check them out. And why don't you tell me yours when you get to class? Take care, and I'll see you in class.